Hello there, welcome to day 21 of Advent of Code 2021. So I have started falling behind. These challenges are getting quite a lot harder than I expected. These videos are slowly going to be uploaded over the next couple of days, and I'm not sure that I'll be able to do Christmas on Christmas Day, but we will see how things go. Day 21, dice rolling. I assume you will have read the description. If you haven't, just head over to the Advent of Code website and take a look at it. So this challenge was quite interesting. The first part, which we'll do now, is quite straightforward. There's really nothing much to it. We just need to simulate the game as it's described, and we go for it. So the way I did that in Go is I just created a little struct to keep track of what the next roll should be. Hopefully this isn't too foreign. So let's see, what do we need to do? We need to increase the state. This is nice because the first roll is 1, state starts off at 0, so this will give us the right result. The 0 value of the die is going to be good. State plus plus, and then we just say if the state is 101, then we roll it back to 1. So like that. And so this should be quite straightforward. If we roll the die 10 times, we're going to get the numbers 1 to 10. And once we hit 101 times, we're going to roll back to 1 and keep going. Cool, so that's pretty straightforward. We need to keep track of the player positions, and so to do that, I just did this. I'm using the example just to start with, because then we can see what the result is supposed to be. We also need to keep track of each player's scores. So again, that's pretty straightforward to do. We initialize them to 0. Cool, and it just says you keep going until a player reaches 100 points. And so P1 is going to be P1 plus the roll, plus the roll, plus the roll, because it's 3 rolls, which we then need to mod 10 to keep it within the loop. Now, there was a little bit of a trick with the mod 10 because on the 10th space, where mod 10 is going to be 0, the score is actually 10. And so the way I did that was I just had another little array called scores, which I'm going to put up here actually, because we're going to reuse this later on. Scores, and it's going to be just that array. It starts off with 10 points on the 0 space, and then just 1 to 9 all the way through. And what that means is you can, it's equals. The score becomes easy to do, right? You just add the scores to it. Then we just need a ending condition. If p1.score is greater than or equal to 1,000, we end the game. Do the same for player 2. So we should be able to just find and replace them all. Not that one, that one, that one, that one, not that one. Cool. So here I'm just going to print out if player 1 wins, then the result is we need player 2 score times. Right, we'll do that afterwards. So just put up player 1 score, player 2 score, and yep, just the scores as well, and we'll see what we get. Which is, so 1,000 is player 1 score, 745 is player 2 score. This should be pretty straightforward. So to keep track of the number of rolls of the die, which we need, the die has been rolled how many times, we need to know that. That's quite straightforward. We just add another variable to the struct. We increase it every time we roll. So then we can just print that out at the end. And then if player 1 wins, we want player 2's score times the roll. And then I'm just going to put these in brackets just to keep it like a little bit nicer to read. And if player 2 wins, we want player 1's score times the number of rolls. Cool, and that's the correct example input. My input for this puzzle is 6 and 2. And so when I pop 6 and 2 into here, into the initial positions, we get my answer. So that was pretty straightforward. That is a very simple simulation of the entire thing. I think the tricky part was now part 2, where you have these quantum dice being rolled. And each roll of the die, you have to basically simulate every possible outcome of everything. Now, my initial observation of this was that we rolled the die 3 times. And we have to take into account every version of those rolls, right? 1, 2, or 3. But if you list out all possible combinations of those rolls, what we move is the sum of the 3 rolls. And if you work out all the combinations and all the sums of those combinations, you end up with just 7 different possibilities at each point. You can either get a 3 or a 4 or a 5 all the way to 9, which would be 3 3s, and a 3 is 3 1s. Now, some of those rolls are more common than others, right? This is the same as if you just rolled 2 normal dice. 7 is more likely than 2 or 12. It's the same idea. And you get this kind of Pascal's triangle-ish sort of frequency for each roll. So this is the summary of each roll, right? Each turn, player 1 is going to move 3 to 9 steps. And it's more likely that they're going to move 6 steps than 9 steps. But so we just need to know those frequencies. But then player 1 is going to move 3 to 9 steps, and then player 2 is going to move 3 to 9 steps, and so on. Now, I sat down for a while and tried to figure out if there was a way to calculate this mathematically without simulating everything. My maths is okay, but it's not amazing. And so, no, I failed. I couldn't come up with a way to work this out mathematically with a formula. And so I had to simulate everything. And so, yes, I simulated every single possible game. And it turns out you can actually do that on a computer without blowing everything up, running out of memory or time or anything like that. So how did I do that? So first, I'm just going to comment this out because, well, you know what? Maybe I'll leave it there. Yeah, I'll leave it there. So a couple of things. Let's figure out how we might represent a game. Now, one way you could represent a game is you could write down what each player rolled on each turn. So for example, if player 1 rolled 6, and then player 2 rolled 4, and then player 1 rolled 8, player 2 rolled 5, player 1 rolled 3, player 2 rolled 6, something like that. So this could be a game. Now, how do we know how much each player scored? Well, we can reuse, no, I can't reuse those variables unless I do this, so I will. I'm going to turn this back into the test example setup again. And I'll bring this down so it's a bit easier to read. So you can still, using this formulation, you can still do everything we did up here, right? We can say, oh, let me see, let me think. My mind's gone blank for a little bit. We can say what the score of each player is. We need a function that will tell us the scores of each player. So what we need is the initial values, P1 and P2. So in fact, actually, I don't need this at all. We need the initial values of P1 and P2. and we need the game. And what we can return are the scores of the the two players, which I will call S1 and S2. So how would we do that? Well, we just run the game again in the exact same way we did before. So P1 for each role in the game, and I need an index for it as well. We say, which turn is this, right? If the index is even, it's so 0, 2, 4, and so on, then it's the first player's turn. Which means if it's odd, it's the second player's turn. Hopefully that makes sense. Yes, I can't call this scores. I'll call this score. So if it's player 1's turn, then player 1 is going to be player 1's position plus the value of the roll, mod 10, just like before. Same with player 2. And then player 1's score, which is now stored in S1 variable, is just going to be the same thing. Plus equals the score of that location. Right, and then we just return those two values. Excuse me for a second. Sorry, I had to sneeze there, and I didn't want to get that on camera. And that will tell us the scores of each player. So if we print this out like this, we will find that with got in the wrong position. We can see that with these specific roles, player 1 is going to have 19 points, player 2 is going to have 12 points. So let me just pop in an extra, I don't know, 5 in here. And player 1 is now, so with this particular sequence of roles, player 1 wins on turn, well, player 1 wins. On turn 7 overall, turn 4, if you just count on player 1's turns, doesn't really matter. But player 1 wins this specific game. And so to count the number of games, we generate every possible game that can ever be played. See if player 1 wins or player 2 wins, and then we count them all up. That is the solution. But there's a bit of a hiccup here. So let's say this game was this, and everyone just rolled 3s. I might have rolled too many 3s. Let's say everyone just rolled 3s. How many games in this universe can have this specific outcome? Well, seeing as there's only one way to roll a 3, there is exactly one game in the entire universe that can have this outcome. And I hope that makes sense. But when we have a game like this, well, to roll a 6, for example, player 1 could have rolled 1, 2, 3. They could have rolled 1, 3, 2. They could have rolled 2, 1, 3. They could have rolled 2, 2, 2, 2, 3, 1, and so on. And so there are 7 different ways that 6 could have come up. And then with this 4, there are 3 different ways this 4 could have been rolled, and so on. And so I hope that makes sense, that what we do is we multiply together the number of ways each number could be rolled, and that will give us the total number of possibilities for how this game could have occurred with all the once you count in all the individual dice rolls. And so I'll make a function called count games. We pass in the game. Now here I'm going to make an int64 just because ultimately the answer is going to be really big, and Go is picky about typecasting, so we'll just keep it all as int64s whenever we're doing counts. We just need a little multiplier here, array. Now for these sorts of things, I like to just not do any arithmetic on them. And so I'm going to start on the 3rd slot. So to roll a 3, there's 1 way. To roll a 4, there's 3 ways. To roll a 5, there's 6 ways, 7, and then it just goes back down like this. So hopefully this makes sense, that we're skipping 0, 1, 2, and then we have 3, 4, 5, 6, 7, 8, 9, all the way through like that. So to count it, oh, let's not do that. So we pass out for each role in the game. We just multiply it up. Multiply role, and we return out. So we count the number of games that can have that specific outcome, and it turns out that there are 15,800 games that can ways that we could have arrived at this specific game. And so that's how you can end up doing a lot less work, right? If we were simulating every individual dice roll, then now that's 3 times as many in-between states that we have to care about. By collecting it up like this, we reduce the amount of work that we have to do. It still takes a little bit of time to run in the end, but I would assume, I never actually tested this, but I would assume that this uses significantly less time to simulate than if we tested every single individual roll. So the next question at this point is how do you generate every possible game? If we just try to generate them all and stick them all in memory, it might be able to do it. You might run out, I'm not sure. And so I thought this was a good time to kind of try out how generators might work in Go. So if you come from a Python background, or I think JavaScript has them, you'll know what generators are when you have yield return or yield return. I'm not sure. Go doesn't have that, but we can kind of simulate that sort of thing using channels. Now, I don't know if this is good practice, best practice, but it's something that kind of works. And so this is what I came up with to do this. So we're going to generate a game. We're going to give it the initial values like this. And what we're going to come back out with is a channel of results. We'll work on what the results are later, but they will have to include at least a game. So let me take a look at my notes because I can't remember exactly how this goes. Right, okay. So to generate the games, first we need this channel. So channels in Go, if you're not familiar with them, they're a concurrency tool. But they're also useful for passing data for kind of passing. So it is concurrency. I think so. In a proper generator, the function actually halts, and the state is somehow stored in memory somewhere, and so the function actually returns and it does stuff. So using channels, what we're doing is we're actually kicking off a coroutine. Is it a coroutine? I don't think it's a coroutine. We're kicking off a Go thread. I think that's what it's called. It's like a lightweight thread sort of thing. So we're actually running our generator in parallel, but it will block on passing data through the channel. So it does kind of stop because it blocks, but it is technically not a generator because we are running 2 different things in parallel. But the semantics of channels in Go means that it blocks and it kind of feels like a generator, and it kind of runs with the same sort of efficiency as a generator, except that it's not actually a generator behind the scenes. So the other thing with this is I will need to use a recursive function here. And if you're not comfortable with recursive functions, this is going to feel a little bit weird, but hopefully it will make sense. So let's see how this is going to work. I'm going to have a recursive function here that I'm going to end up calling. At the end, what I'm going to do is I'm going to run. So Go is in Go means to kick it off in a new thread. I return the channel, which means I can pass things back like that. So let me just double check that I haven't missed anything here. Good. Okay. So this is the template for generating my games. Calling this function is going to give me back a channel, And as I read off, and what I'll be able to read out of that channel, what I want to read out of that channel are all the possible games in this sort of scenario. So how do we do that? Well, each game is going to need to generate every possible state. So every number from 3 to 9. Now with slices, if you just append to the slice, sometimes weird things happen. So I did run into this when I was writing this the first time, and the slices that were coming out of my channel were all mixed together. I'm not sure what I did wrong, but to be safe, what we'll do is we're just going to copy the entire slice. So we're just going to copy the slice. We're going to make a new slice that is one longer than the input slice, like this. We're going to copy into the new slice all the values in the old slice, and then assign the last value to be the next number that we've generated. So you see here when we first call it, we call it with a nil slice, which is an empty slice. It's the same thing in Go. And the first time this runs, we're going to create next is going to be a slice of length 1. And we're going to assign to it 3 the first time, and then 4 the second time, then 5, then 6, and 7, 8, and 9 all the way. So next at this point is going to be the sequence of the game so far. So here we can reuse our old function. We're just going to say score 1, score 2 is going to be work out the scores for, and I need to pass in the initial states, so P1, P2, and the game. So I have the scores of this game so far. The rules say if the scores are greater than or equal to 21, the game finishes. So if the game finishes, this is what we want. We want this. If the game is finished, one of the players has won, they've reached 21 points. We're going to pass that down the channel. So sending into the channel a new result of the game. And this is another reason why we copy it, because we want these to not interfere with each other. And the scores, so we don't have to calculate them again. If the game hasn't finished, however, then we need to generate the next turn. And the way we generate the next turn is we recursively call this function itself, but with the current game state passed into it. So now what it's going to do is it's going to generate the second turn. And if no one has won on, if neither player has won on the second turn, we generate the third turn. And so what you'll see is that this function is going to return every possible game that generate turns until a player wins, and it's going to keep going, and you're going to end up with every single game. So just to show how that works, we're going to call that generator. We're going to pass in the example state to start with. And we're just going to read out of it, see what we get. We'll do it a couple of times. So hopefully this makes sense. We've generated the first game. The first game on the 7th turn, player 1 reaches a score of more than 21. So the loop terminates at that point because you're not recursively calling. So it's going to start unwinding that recursion until we end up at 3, 9. Then we start rolling 4s for the second time, and so on. So right now, these games are all 7 long, but at some point, we're going to start getting games that are either shorter or longer. Okay, so it looks like at this initial state, that doesn't happen. So I do know that at 0, 0, I believe, we get something a bit more interesting. Right, so at 0, 0, you'll see that. And by the way, you can work this out, right? So if both players start on 0, player 1 is going to get 3 points on the second turn, and then another 3, so that's they're now on 6, so that's 9 points. Another 3, they're now on 9, so that's 18 points. Another 3, so 9 plus 3 is 12, so 2, so now they get 2 points, around 20. And then finally on this turn, they're going to hit the 5 and get 25 points. 25 points, and win the game. So some games last longer, some games last shorter, but this truncates, right? Once a player has won, it stops, so we don't need to keep generating more turns for that universe, and we go back. Now, the other important thing, of course, is getting the number of games that end up in that state. So we can use our old function, count games. Dot game, confusing names, and maybe we'll just pop it at the end there so it's a bit easier to read. There's one game that ends up looking like, there's only one possible way that the universe can end up looking like this when all the rolls are 3. There are 3 possible ways the universe could go like this, right? These are all, the players have all rolled 1s, and then on the last turn, the player either rolled 1, 1, 2, or 2, 1, 1, or 1, 2, 1. Right, so which is why there are 3 different ways that this game is possible, 6 different ways this game is possible, and so on. And in fact, if we generate a couple more games, we'll start seeing things going a little bit bigger like this. Okay, these games are all kind of boring. They're all stuck with that initial thing. But yeah, once games start getting a bit more complicated, there are more 6s or more 5s going on, then suddenly there are a lot more ways for the game to look like that. But that is basically, yeah, once you have a way of generating every possible game and a way to work out the score of those games and to count how many possible ways that that game could have occurred, now what you need to do is just count them up. So these need to be N64s, of course. So I just have player 1, player 2, scores, counts, so it's the number of wins. So we just say if game.score1 is greater than game.score2, which means player 1, 1, then we'll just increment player 1's counts. They've won that many more times. Otherwise, player 2 has won. And we count that many number of times. And then here, I'm just going to print out the result so that we can see it run. Whoops. This needs to be an infinite loop. And you can see it's generating all these, or every possible game. And in each case, it is adding those counts together, which isn't being printed out. Now, it looks like it's going kind of slow, but actually this slowness is due to the printing and not due to the actual algorithm. Because look, at this rate, it's going to take a while for it to get to 9999. However, if I just reduce the amount of, because it takes a while, so I still want to print something, but if I reduce the amount of printing that this does, so what I can do is I say if, I'm just going to print every time the first number changes. Last equals game.game 0, like that. Here I need to print out wins. So it does take a little while, but it is definitely going faster than it was before. And you'll see that some combinations go faster, some combinations go slower. Now there's one more problem here, is that this. I never told you, idiomatically in Go, you would close a channel to tell Go that work is finished and we don't need to keep reading from this channel anymore. And there's a couple of ways you can check that, but one way is to just add an OK here. It kind of looks like a map. And the OK will be false if the channel is closed. And so once the channel closes, which means there's no more information to send down this channel, we're going to break out of this loop and we're going to print out the wins. And then here we just need to figure out when we're going to close the channel. And an easy way to do that is just to say, if it's nil here, we close the channel. What does that mean? This, because this is a recursive function, every time we call this, this is not going to be nil. The only time this is nil is when the first recursive call, or the first call of the function finishes, right? And that's that bottom level of that recursion. And so this is just a way for us to kind of figure out if we are that top level. And if we are that top level and we're finished generating stuff, there's no more things to generate, we close the channel, and that signals to the main routine that we are done generating every game. There are no more games to check, and you can break out of your loop and print out your answer. And so with that generator going and us counting the games, once this finishes, you will see that, oh, this is 0, 0, eh? Dang it, this is 0, 0. You have your answers at the end, and that's the sum. So with the example data we have here, which is where player 1 starts at 4 and player 2 starts at 8, we just let it run a little bit. It's going to count all the games, and we're going to end up with so at some points you can see that like 5 and 6 went really fast, and I'm guessing it's because player 1 lands on like big numbers, right? They land on 9 and so on. Whereas at some of these bigger numbers, maybe they land on 1s and 2s, and therefore the game has to go on for longer before a player wins. But here we go. We are finishing off all those final games, and once they finish, we get the number of games that each player has won, and you'll see that these numbers here are the same as these numbers here, which is what we want to see. And so with my input, which is 6 and 2, as you can see here, I just pop that in. And with different inputs, they're all going to have slightly different characteristics, right? Because you're going to land on different numbers to start with. But we generate all of those games. We count them all up. And you will see that this is my answer. And so, yeah, that is basically how I solved this one. I didn't think that, two things, I guess. One, I didn't want to generate all the games because I thought it wasn't possible. And two, I am surprised that it is possible, and that is a way to do it in a relatively reasonable amount of time. And you can see that's my answer. So if you want to attempt this, I hope that kind of brief intro to sort of channel generators sort of thing made sense to you. All the work happens in this recursive call to generate all the games, and everything else kind of is just about reasoning about the problem and a little bit of maths. So I hope this was helpful for you. Thanks for watching this video, and I will see you again another time.